And thank you very much to the organizing committee of PASC, and in particular the materials division, and Nicola Mazzari for inviting me here to speak today. So the title of my talk is Random Explorations in Material Structure Space. This has two meanings. As you heard from the introduction, I've introduced an algorithm based on random sampling of configuration space to predict new materials. The other meaning of the random explorations of material structure space refers to the sort of discovery mode with which I've applied it. So I probably am a frustrated experimentalist. And when I started my PhD with Mike Payne in Cambridge several years ago, now I wasn't sure whether I wanted to actually work in experiment or in theory. My supervisor, Mike Payne, arranged a project where I could do both. Now, unfortunately, in the first 6 months, the electron microscope I was supposed to be working on was broken. Vacuum problems. This is pretty much the generic problem with experimental physics. You don't have a vacuum. You're looking for leaks. So I wasn't able to get started in experimental work, so I got coding, and I didn't really stop. And I'll tell you, I'll explain what I've been up to since then. Now, the frustration of being a theorist, at least at the time, and computational physicist at the time when I started my PhD, was that it was very, very hard to actually discover something new computationally or theoretically. The preeminent mode of operation of a theoretical condensed matter physicist was to help experimentalists explain their strange wiggles in their curves that they took off their measurements. But I wanted to do more than that. So I'll take you through the steps in my sort of day-to-day work. On one side, we do start sometimes with pieces of paper and writing down equations. Now, that equation up there is one of the key equations of density functional theory. And it's the way we turn an essentially intractable computational problem into something we can actually get some reasonably sensible numbers out of. So density functional theory is what we mean when we say we're doing quantum simulations. Now, if you're very, very lucky, you get to write down an equation as beautiful as this. This was Walter Kohn who wrote this down, who sadly passed away just a month or so ago. The rest of us, if we do theory, what we tend to be doing is just adding a small perturbation to one of these beautiful equations. So in my case, with Francesco Mauri, in my early postdoc years, we figured out how to add magnetic fields to density functional theory, or a weak magnetic field to density functional theory. And that allowed us to develop a technique for calculating and predicting magnetic resonance spectra. Now, this was something that was reasonably well established in the chemical community for molecules, but simply hadn't been done before for solids and crystals. Now, we're very fortunate that at about that same time, the experimental technique of so-called solid-state NMR was really taking off, and there was a group of young scientists who rapidly took on the method that Francesco and I developed computationally, and now it's an integral part of an experimental science, solid-state NMR. They largely do the calculations themselves, and I don't have to do that. Now, if you've written down your theory, these beautiful few hours where you're writing things down and doing integrals and all these fun things that are, if you like mathematics, are really good fun to do, that's over very, very quickly, and then you have to sit down and write the code. And if I'm honest, I would say the vast majority of my scientific career has been spent, probably as many of us here, spent coding and realistically debugging code that I'd written before. The biggest effort that I've been involved with was this CASTEP code that was mentioned previously. This is a so-called plane wave pseudopotential density functional theory code. There are other versions around there, VASP, Ab init, Quantum Espresso, which many of you will have heard. If you've been going to the materials session in this conference, you'd have heard a lot about this already. This was a project that I took on with 6 other, at that time, young academics or young postdocs to rewrite or completely rewrite an existing code base based on existing old academic version of STEP. There was a parallel version that was sponsored, CTEP, which was sponsored by the Edinburgh Supercomputing Centre, and there was also a code that was moving to become commercial at the same time. The group of us had just decided that each of these 3 sets of code were just not going to be suitable for our future research development. I wanted to do things like implement more complicated perturbation theory and also make sure I had a code that was robust enough to do what I'm going to talk about in the rest of the talk, high throughput computation. And the existing code just simply wasn't up to that. In those days, I think there are some people in this room who have run these very old versions of CASTEP. You used to have to compile each time for each crystal structure that you ran for. You had to hardwire into the parameter set the size of your arrays and dimensions. This was not suitable for high throughput computation. So several years of my life later, we had this very nice piece of software, which is now pretty widely used, particularly in the UK, because it's free in the UK, but elsewhere it's more commercially available by a company now called Biovia, who's part of Dassault Systems. Now, it's all well and good having a nice piece of software, but if you haven't got computers, then it was all for nothing. And the other nice coincidence at the time I was going through my part of my early career was the rapid development in computer hardware. As we heard yesterday, we can't really, as scientists, take much credit for this because this was being driven at that time by the growth in PCs and subsequently mobile phones, and I saw in the future going to be driven by Internet of Things or whatever. We'll see how that turns out. But the fantastic thing that happened was that multi-core chips suddenly came onto the scene, and that meant this exotic parallel ability to do parallel computation suddenly was available to everybody in their workstations or desktops. Everyone was doing parallel computing. Now, if you combine a nice new theory and you've written a really good code and you've bought a shiny new computer, in principle, you should have some new sort of scientific superpower. You should be able to do something that no one else has been able to do before. And traditionally in our field, these superpowers have been directed in several different directions. One of them might be, one area, particularly in quantum chemistry, is focused towards doing ever more accurate quantum simulations of nature, but necessarily that restricts you to rather small system sizes. Another approach is to stick at roughly the same level of accuracy or precision, but tackle more complex systems. And there are people who are going as far as applying our methodologies to biochemistry. This involves developing other computer codes, such as the one-step code that we heard about yesterday in the material session that allows you to do order n scaling. My angle, having been starting off in an experimental group, was to work on calculating new properties, spectroscopy. And this slide here is actually probably one of my most favorite slides ever. It may look pretty mundane. You've got a bunch of wiggly lines. But what we've got there is a theoretically computed NMR spectra laid on top of an experimentally measured NMR spectra. And fantastically, hopefully if you're sitting at the back, you can't tell the difference between them. But that's not really why I really like this slide. The reason I really like this slide is that the person who did the experiment, Sharon Ashbrook, who was my colleague up in St Andrews when I was there, is a solid-state NMR spectroscopist, and she both did the measurement and did the calculation herself. And for me, this is the success of having developed a good suite of software, that it's in a good enough state that you can hand on to other people and they can do as good a job. In fact, I'm pretty sure a better job than I could do of using it to understand their spectroscopic problems. Okay, so this is mostly the way that most of us work. New properties, more precision and complexity. But something has changed. On top of these, the existence of these multi-core machines, people started putting lots and lots of these multi-core chips together to make very large clusters. And as we heard yesterday, high-performance computing centers are not the only place that computing is done in this world. And what I put here, this is some French cloud service. I think they're called cloudwatt.fr. But there's probably thousands of these kind of startups around the world doing cloud, basically commodity computing. And I tried. This is a number. A couple of years ago, I estimated for how many servers Google had. Each of those having maybe 20 or 30 compute cores in them. So maybe something like 3 million. They probably got even more now. Compared to what we're using, this is a lot of computing. And strikingly, what does Google do, or what do we do with Google's servers? And it's search. That's how they started out. Then they serve us adverts in response to our search. Now, around the same time as I guess Google was really getting going, there were other scientists who are starting to think of how to use this computing in a different way than trying to do large, complex calculations or pushing things to higher precision. Okay, and this was the use of these machines for high throughput computing. Again, we heard in the context of the Schlumberger work on analyzing seismic surveys that this is a very, very productive area to work in. This was something that was caught on very early on by Gerd Sieder in MIT, and he's the originator of what was called the materials genome project, but he had to adjust his name in response to it becoming actually a much bigger initiative in the US. And the basic idea behind that was realizing that we've got these very nice codes, nice polished codes like CASTEP or the VASP code that were very easy to use. You can input a structure and out will come some reasonably sensible answers. And there's also, over about 100 years or so, experimentalists working in X-ray diffraction or electron microscopy had developed databases of existing crystal structures. And many of them had not been treated quantum mechanically before. So the idea here was to use high throughput computing to work your way through the existing databases, calculate many properties, compare relative energies and stabilities, but also calculate properties, functional properties, whether in particular in the materials project to look for good new battery materials, in particular battery cathodes. So this has been a very successful, and it's a very well-known now, approach to using high throughput computing. Now, roughly at the similar time, myself and others, such as Artem Oganov, have been taking a different tack, a different kind of high throughput computing, but actually very similar. So the difference was where were we going to get our original structures from? So the question that we were trying to ask or answer was this key problem. I would say it's a central problem in condensed matter physics. Largely, how do large collections of atoms condense? How do they arrange themselves in space? That's a very general statement. That, in principle, encompasses predicting the crystallization of rock salt to predicting protein folding. It's all the same problem. It's the arrangements of atoms in space so as, in some sense, to minimize or get their energy to be as low as feasibly possible. So this is the key question. We have a bunch of atoms. How will they arrange themselves in space? This has been thought of as an intractable problem, and I'll explain why that has been traditionally thought of being a very difficult problem in a little while. But first, I mentioned that the key thing here was comparing energies. Energy is the central property that we get out of our so-called total energy methods. If you have energy, you can calculate many, many things. But the question is, where are you going to get that energy from? And there are two traditional ways of doing that. One of them would be what I would call an interpolative approach, based on looking at what we know already and maybe fitting a function between the points that we have already. Now, nowadays, this would be called machine learning. Okay, but previously, this was fitting of empirical potentials and so on. In fact, it's been very nice over these 2 days to really see the fusion between these two different approaches. I think now the only game in town for making new empirical potentials is something based on the machine learning techniques. But these are fantastic and potentially very fast if you're then going to sample or ask questions that are in the domain where you already have the information. So if you're doing an interpolative problem. However, as soon as you start striking out into the unknown, you can rapidly come unstuck in these problems. So the other approach, if you want to be predictive, to go where we haven't gone before, and that's really where I wanted to focus on, is you really must appeal to the models that we're absolutely confident in. And the model that we're really confident in, that nature adheres to as well as we know in pretty much all situations, is quantum mechanics. And so we can be really confident that if we do a good job of implementing a solution to Schrödinger's equation in our computer codes, then it should equally well work, say, in the center of a planet far, far away in another solar system. Okay, this is a very transferable solution to our problems. And I'm going to follow up on that idea towards the end with some examples. But now let's just think for a second why this is thought to be a very difficult problem. And it basically comes down to the problem of the so-called curse of dimensionality, that material structure space is very, very, very big. We can very quickly get an idea of this by just thinking, how do we specify positions of atoms? If we have one atom in space, we just need 3 numbers to locate it. It lives in 3 dimensions. If we have 2 atoms, they live in 6 dimensions, give or take some symmetries that you can 6 dimensions, give or take some symmetries you can remove. And by the time you got to 3 atoms, you're living in a 9-dimensional space. Now, if you think that your function that you're trying to evaluate in each dimensions maybe has 10 minima in each direction, by the time you've got to 3 atoms, you're a billion minima to explore and examine. And people just thought this was not going to be it was not a goer. Yeah. So if it were genuinely the case is that you had 10 minima in every dimension and all minima was equal, then as you increase the number of atoms in your system size, you get this exponential growth of possibilities. And the only real true way of doing global optimization on this is to visit everyone and compare them. And this is not going to work. And the number of atoms that we really want to deal with are probably 10 or 20 or 30 or 40 or maybe 100. If you're doing protein folding, you've gone off the scale. So this is it was thought to be just impossibly difficult. Now, it turned out, fortunately, I hadn't thought very deeply about this when I started trying to solve this problem. And so I naively decided to do structure prediction using first principles and just doing what I call a random sampling of configuration space. So randomly putting atoms into your box, allowing your box to be a random shape, your lattice parameters to randomly variable, and then hitting go on my code AIRSS Ab and saying go downhill. Okay, and then do it again, and then do it again, come back the next day and just compare all my different structures. The first application I did to this was carbon with 4 atoms, and overnight I was able to predict, actually, go beyond the state of the art with what was known about carbon phase. So it turned out to be possible. Fortunately, I hadn't read the literature beforehand. But now, some years, as years passed, of course, every time I gave a talk about this, people would challenge me as to why does it work, what I'm doing. And the argument that we have now that appears to make some sense is that it actually matters exactly what the energy landscape is that you're trying to optimize on. So global optimization is an unsolved problem for an arbitrary landscape, arbitrary energy landscape. There's no right answer to that. But you can make progress by thinking about the particular landscape that you're dealing with. And the particular landscape that we're dealing with is atoms interacting with each other through the laws of physics. Coulomb's interaction, so electrostatics and quantum mechanics with kinetic energy. These are terms, energetic terms, that are fairly smoothly varying in space. They don't suddenly switch on and off. Okay, so your energy landscape, to some degree, is smooth. Now, obviously, so this is a one-dimensional slice of a smooth energy landscape. And what you see very quickly there is that if the gradient of this landscape is constrained, it can't get too steep, then the only way to get deep in your energy is to travel a large distance. Now, this is an observation not made by me, made by others who study energy landscapes, that there's a correlation to the size of the basin in your energy landscape and the depth of your basin in the energy landscape. It doesn't mean it doesn't mean that the deepest basin is the widest basin, but generally speaking, a very shallow basin will likely have a high energy and a very wide, a very wide basin will have a low energy. So there's a correlation. This is potentially something that's going to work in our favor. Now, in this case here, in one dimensions, a very sensible strategy for finding the minima is just to do what I said, just randomly drop some balls in and let them roll downhill to the bottom. And that's what I would suggest. However, there's a second part to the argument, and that's the question: how many big basins are there? I may have said that big basins are deep, but there may be no big basins. It may the whole of the energy landscape could be filled up with lots and lots of tiny basins, and then one sort of medium-sized one that you've got to somehow locate. So this is where some numerical experiments by Jonathan Doi and Claire Mazin, the two theoretical chemists in Cambridge at the time. I don't know where Claire Mazin is, but Jonathan Doi is now in Oxford. They did some numerical experiments where they actually tried to measure the size of these basins, of these energy basins in this high-dimensional space, for Lennard-Jones, a very simple interaction potential. Simplest one, it's 1 over r to the 12 minus 1 over r to the 6, but interaction potential. They considered moderate numbers of atoms arranging themselves as clusters and measured the size of the distribution of sizes of basins. And the conclusion they came to is that the distribution, well, how might the distribution be? The typical distribution that we find in science is a normal distribution. It's normal, okay? It's a Gaussian with some mean, some average, and some width. And the chance, if you've got a normal distribution, of having a very big basin or a very small basin is basically 0, because the e to the minus x squared tails kill off very, very quickly. So that's sort of the not even thinking about it idea of how these basins might be distributed. There'd be a mean basin size, and then they'd be distributed in some normal way. What they found was that there was a power law distribution of basin sizes. Now, those who are physicists, particularly statistical physicists, will realize a power law is indicating some sort of fractal structure to your energy landscape, and that's what they proposed. They proposed that the energy landscape was in some sort of fractal, had some sort of fractal nature. And so here, the picture they drew was this, an Apollonian packing of spheres. They didn't actually draw this exact picture, but this was their idea, is that you have some big spheres or big basins, and then in amongst the big basins you pack some medium-sized ones, and so on all the way down. And this packing has a power law distribution of basin size. So this is their cartoon or model for the energy landscape looks like. So putting it together, they're suggesting that there are some big basins, and then it's also suggested that these big basins probably are the deep ones, or you at least need them to be big in order for them to be deep. So these are two things in our favor if we just do the very simple throwing your atoms into your unit cell and going downhill and sampling many times. You have a reasonable chance of hitting a big basin, and you've got a reasonable chance, therefore, of getting a nice low energy structure. So now, it doesn't mean that, so in this case here, this picture here of these very big basins and some medium-sized basins and so on, it doesn't mean that the lowest energy structure is going to be this biggest basin. It might be this one or even this one, but they're not the teeny ones. They're not the impossible to find ones. So we have some chance. Well, it's okay. So this was used as some backup to why our very simple approach was working. I then went on to do some numerical experiments of my own, but not based on clusters, based on actual crystals, because I was interested in predicting solid-state things, crystal structures. And so I used, again, the Lennard-Jones potential. The Lennard-Jones it's not a quantum mechanical potential, but it shares some of the features of quantum mechanics in that it's smooth. And so what I did here was I increased the number of atoms that I was throwing into my random box, and the shape of the box was initially chosen to be random, and also, as I'm minimizing, I'm allowing the shape of the box to change as well. And I repeated that experiment many times, and I counted how long it took me, as I increased the number of atoms I'm throwing into my box, before I encountered what I know to be the ground state. Because at Lennard-Jones Crystal, we know that the ground state is a hexagonally close-packed structure. So I know what the target is in this case. This isn't discovery, this is testing. We know what the answer is, and I looked at how many times I had to throw my atoms into the box before I found the ground state. And for people who thought that structure prediction was a difficult problem, this should be a shocking graph, because this isn't a log linear graph, this is a linear graph. This is showing, at least for this range from a few number of atoms up to about 120, that the difficulty of the problem is growing only linearly in this case. Now, as you go to even larger systems, actually it does start to take off. But what you can, and get very big, you can see here actually, as you go from 2 to 4 atoms, it gets easier. So as you increase the dimensionality of a space, it's getting easier. How do we interpret that? Well, imagine if you're walking in a one-dimensional mountain range and you're trying to get to a valley on the other side of the mountain. You've got no choice but to go over the mountain. But in 2 dimensions, you go around the mountain. So there's more some freedom leaks into the problem as you go into higher dimensions. And this, in the early stages, works in your favor and simply makes the problem easier. At some point, I would suggest that the target basins get to a sort of maximum size, and then they start to become disconnected, and then you enter a combinatorial regime where genuinely the problem is impossible and intractable. But for us, being able to treat systems up to about 100 atoms or so, this is a good place to be for crystal structure prediction. And what I've plotted here are densities of structure states for increasing numbers of atoms. And you can see that as you go to, so 500, the red example is 512 atoms. As you go to this very large limit here, you do start to get this, everything clusters towards this very disordered state, essentially the glass or jammed random state here. But the thing about the thing that makes the random sampling work is this very, very long tail which goes down to low energy. Okay, and you see that very, very strongly. For 128 atoms, you've got these strong peaks down at low energy. These are not what you would expect if it was a difficult problem. This is it showing the random sampling working well. If you do these kinds of sampling for the Lennard-Jones crystal for, in this case, 256 atoms, you can start to visualize you can try and visualize your data. And in this case here, I've plotted the volume of your resulting structure versus the relative energy compared to the ground state. And for 256 atoms, 1 in 200 times, I've hit a close-packed crystal structure. It might not necessarily be HCP, it might be face-center cubic as well, but they're basically the same in energies. And then as you move up in energy here, up here, you see this is each atom is colored using this Atomize software. Each atom is colored according to its environment. So if it all looks lots of different colors, the environments are all different. It means it's some sort of random structure. But when they're all the same color, you're crystalline. So up here, you've got your random structure. Down here, you've got your pure crystal. In the middle here, you've got sort of mixtures between amorphous structures and crystalline structures. And the striking thing in this plot was the emergence of these blips. I wasn't expecting to see patterns in this structure. And what was that? Well, when I looked at what those structures were in those blips, you realize that these are actually discrete numbers of defects in your structure. These are vacancies that were appearing. 1, 2, 3 vacancies appearing in your structure, and these come in discrete chunks of energy. So the nice thing is, in principle, if we could do millions of samples for 256 atoms using quantum mechanics, not only would we be able to predict crystal structure, we'd also be able to predict microstructure. And microstructure is what controls the real properties of materials, certainly structural materials. Now, this was a test case. This was Lennard-Jones. This is a very fast potential. I could run this on my laptop. We can't do these kinds of plots for using things fully quantum mechanically, but I will show you what we can do. Now, I mentioned there were these two routes, the sort of the first principles route or the empirical potential route. Now, it turns out that, of course, lots of people had thought about structure prediction before, but they were led down the reasoning that because this is a difficult problem, I'm going to have to evaluate energies many, many times, then I need those energy evaluations to be very cheap, and so I must use an empirical, fitted potential, because that's the only way of calculating these things quickly and cheaply. Quantum mechanics is too expensive. It turns out this was a big mistake on their part, because although the energy was quick to evaluate, the shape of the energy landscape was different, or in many cases, for many empirical potentials, was different. And it has many false minima that you then spend your time, although you're evaluating each energy quickly, you're spending a lot of your time searching through configurations which just don't have any relevance to reality. And to illustrate this point here, I recently did a simulation for 8 atoms of silicon and sampled using density functional theory or quantum mechanics 5,000 times, and using the empirical Tirsoff potential, it's a well-known potential for silicon, 10,000 times, and I plotted a similar density of states than what we saw before. And the first thing you can see, the shape isn't the same. The second thing you can see is that the red quantum mechanics has a much higher weight down at low energy than the Tirsoff potential. So if you had actually done random sampling of just like uniformly sampling configuration space and looked at a distribution like this, you'd have said, I can show that random sampling won't work because the weight in the tails is too small down at low energies. And you'd have rejected that idea. And indeed they did. And so the route that the people who've been working with empirical potentials took was to use more sophisticated algorithms based on learning, such as genetic algorithms or particle swarms or and basin hopping. Because they needed to make sure they were only operating down in the low energy regime. Whereas random sampling, the contrast with random sampling is it's not a learning algorithm. Each shot is not correlated with any other shot. So it finds a low energy configuration. It doesn't spend extra time sampling those structures near those low energy configurations, which a learning algorithm might do, to try and drill down to the very lowest energy. Instead, it just keeps taking very uncorrelated draws all over configuration space. Now, from the point of view of getting quite a low energy structure, a learning algorithm is a good idea, because you drill down nearby to a nearby low energy. But from the point of view of discovering all there is to discover, you want a broad sampling. And so this is where random search has really had its strength, and it's been very capable in discovering new things that people hadn't suspected before. Okay, so pure random sampling is what I've been talking so far, where you just put your atoms in your box and you relax downhill. Now, you always want to do more. So say I can do 12 atoms quantum mechanically with random sampling. Someone will come to me and they want to do a system with 24 atoms in the unit cell. Well, how am I going to do that? Well, there are ways that we can, by hook or by crook, speed things up. So this is our mantra. If you don't know anything, you should use completely random structures. It's rare. Well, actually, as a physicist, it's often the case that you know nothing. But if you're a chemist, it's quite common that you've got some idea as to how the atom should be arranged in configuration. So a chemist might actually come to the problem already knowing roughly how atoms should be arranged around each other. If they were molecular units, for example, trying to find ice structures, then the sensible thing would be to throw water molecules into your box at once, rather than the atoms of hydrogen and oxygen separately. Or if you're looking at inorganic system, there are particular distances that will be unfavorable in your configuration. So, for example, if you're doing sodium chloride, all sodium chloride structures where the sodium is next to the sodium are going to be very, very high up in energy. So what you can do is pre-screen your random structures so that you exclude any structures which have these bad clashes between the atoms. Another very powerful technique is to use symmetry. Most crystal structures are observed to have at least some symmetry. So even if you've got one additional symmetry operator on top of the identity, you half your number of atoms or your number of degrees of freedoms you have to deal with. And if you've entered the region where your basins have reached their maximum extent and things have started to go up very, very quickly and more difficult, then halving the structure, the space you've got to search in is a very, very important thing. Another, and probably the most useful scientific application of these structure searches is when you start to combine with experimentalists, where experimentalists are able to measure some things about their problem. For example, it's a very common situation where X-ray crystallographers, if they're doing powder X-ray crystallography, which is where all the crystals are pointing in different directions, they're able to figure out from the positions of the peaks in their diffraction spectra the shape of the box that your atoms are in. But they find it much harder to find out how the atoms are arranged in that box. But if I know the shape of the box, then a constraint I can put into my search at the beginning is just to say, okay, the box is this shape, and then I put the atoms in. And it turns out that easily an order of magnitude simplifies the problem. Because when you don't know the shape of the box, you're having to search through every possible shape and configuration and long thin cells and short flat cells and so on. It makes it a lot more difficult to search. So if you know the shape of your box, you're in a very good situation. So we've had some really nice collaborations with experimentalists where they'd reached the limit of what they could do with their standard crystallography tools, and with a bit of quantum mechanics, we're able to take them a little bit further and get some science from their results. Okay, I'm going to have a couple of slides where I show you what an input file looks like in my for a random search, and what the random structures look like before they've been turned into ground state structures. So these are on this side here. This is a structure that hasn't been, the energy hasn't been lowered by putting it into a quantum mechanical code. This is the initial starting configuration that we have here. And it's generated using these commands. It says, okay, I want a box of roughly 11.8 angstroms per atom. The ratio of atoms I want is 1 boron to 1 nitrogen. And here I want 128 copies of that. I'm not going to use any symmetry. And here's this little matrix which tells me I don't want boron atoms to be very close to each other, or nitrogen atoms, but I wouldn't mind if boron atoms were near to nitrogen atoms. It's a kind of very simple empirical potential, but it's absolutely minimal. These are hard spheres, so I don't rigorously enforce a minimum. I'm not minimizing a function here. I'm just satisfying a constraint. That gives enough freedom for diversity to mean you don't always get the same solution each time. Okay, and out pops from my algorithm an initial random structure that looks like that, which you can feed into a code like CASTEP, and you get something that's rather low in energy right from the start. Similarly, if you want to, if you're dealing with molecules, you can take units and throw those using symmetry. In this case here, these are some space groups into boxes. This is a way of searching for polymorphism in molecular crystals, which is a very important problem for the pharmaceutical industry. We don't even in advance need to know what the ratio of atoms that we have in your system. You can use what are called Maxwell plots or convex hulls as a graphical construction that shows you which are the stable compositions. So what you do basically is you do lots of different calculations for different ratios of atoms, and you plot the so-called formation energies of each of those configurations. So the formation energy in the carbon and hydrogen system is the rate. So if you've got methane, you calculate the energy difference between methane and what the carbon and hydrogen atoms on their own would have been, and then you divide. The key thing to make it work is you divide through by the number of components that you've considered. So in the case of methane, there's 1 carbon atom and 4 hydrogen atoms. You divide by 5, and you just plot it on a graph, and you keep plotting, plot, and then you draw a convex hull around those points, and the points that are on the convex hull are stable configurations. The points that are off the convex hull, for example, these points here, thermodynamically would decompose into neighboring configurations. So in this case here, this is carbon and hydrogen system at 0 pressure, and it detects that methane is a good stable composition for carbon and hydrogen. Now, we know about benzene. Where's benzene? Well, benzene actually, most of organic chemistry is actually metastable, and so they're living up here above the hull. But very nicely, we're doing random sampling. I've not put a particular preference on the lowest energy structures. I'm also picking out metastable structures as well. Now, if you apply a little bit of pressure, you squeeze the system together. Actually, you can tip the balance of the chemistry, so you start to get other compositions becoming stable. Methane remains stable, but you get a CH2 composition here, these long alkane chains, and also a CH composition here, which is exactly the graphane that was recently proposed and found experimentally. So these just, at high pressure, you drive it. You have other thermodynamically stable compositions which have carbon atoms joined together. And you can go further than that. You can start combining 3 species together. And here use the so-called ternary plotting system. So this is up here you've got 100% nitrogen, here you've got 100% hydrogen, and here you've got 100% carbon. Now the point of this slide here is to show what would happen if you did the sort of the data mining approach, and what happens when you're doing random search. And this was, for me, this was just an arbitrarily chosen system. I wasn't looking for a system that would show up anything particularly useful, but what I did is I downloaded the 166 carbon, hydrogen, and nitrogen structures in the database, the ICSD, that have been found already, and I calculated the total energies of them, and I plotted them on this ternary convex hull. The circles are stable compositions in this case, and the red and the squares are unstable. And the darker green they are, the lower down they are in your convex hull. To my surprise, you find as the stable carbon-hydrogen system is C19H34. That doesn't look like methane to me. Why did that happen? Well, actually, there are no methane structures in the ICSD. In fact, there is one methane structure in the ICSD, but because it's difficult experimentally to find out where hydrogen atoms are, they didn't put them on. So it was a methane structure, but it was naked of hydrogen. So when you put it, so it didn't come out as a carbon hydrogen system. And indeed, this follows through to the various, well, at least it may have changed now, but in January, this followed through to the materials project. They had CH2 as the stable composition. They also haven't got methane. So it means any project you're doing based on data mining, you've got the danger of actually missing some important compositions which will steer what you think is stable or not stable and affect your predictions. Now, even just a little bit of random searching is going to come up with methane. It's very easy to find methane. So I would suggest that in the future, you certainly want to do both. If you're doing data mining, you should throw in a few random configurations as well, just to fill up the space of possibilities. So you can see here the coverage for the data mined coverage is rather sparse in this configuration space. It's only the ones that people have happened to measure and put in the database. But computationally, you just explore the whole space and you actually start to see some interesting structure. You find some new stable compositions up here that are not reported. I haven't published that yet. But so it allows you to, even if my methane structure isn't the right methane structure, at least I've got the chemical potential roughly correct for comparisons with other ones. So it's important, I think, to do some of this unbiased sampling. OK, so I'm going to talk a little bit about novel algorithms that we're developing at the moment to try and improve random search further. So the current, I mentioned that you might want to use chemical ideas to build other structures. And molecules, building more complicated structures out of molecules is a good starting point. But also you start to learn when you look at crystal structures, there's other hierarchy in structure. Okay, for example, there are units, the recognizable units that structures are made up of. And a classic example is the case of boron. The ground state structure of boron, alpha boron, is obviously made up of icosahedra. You can see this with your eyes, eyes here. Everyone knows that studied this knows that boron is made up of icosahedra. So the obvious thing, if you want to find other polymorphs, other arrangements of boron, is to throw icosahedra into your unit cell and relax those. And indeed, that is a very good thing to do, and it works very well. But this only really works if you know that there are icosahedra in the boron structure, which we do know. But what if you wanted to automate this process and for it to automatically detect this kind of hierarchical structure as you're doing these random searches and use that to build other more complicated structures? There's a problem in this case that if you use so this structure here is produced by looking at by drawing lines between all atoms that are closer than 1.9 angstroms. And you get a fully connected network here. But if you shrink the threshold down a little bit to 1.7, you end up with these dimers. And these dimers are between the icosahedra. So the shortest distances in this structure are between the icosahedra, not within the icosahedra. So just a measuring approach like this doesn't extract the icosahedra. So for a long time, I've been trying to puzzle as to how can we automatically computationally detect the existence of icosahedra in boron. And I have a very nice collaborator in Cambridge called Sebastian Arnott who works in complex network theory. And eventually, a conversation over coffee, this universal scientific fuel, produced one word from Sebastian, and the word he said was modularity. Okay, so this is a technique that they use to cluster social networks. Okay, it was introduced by Newman and Girvan well, there are different approaches, but the approach that we're used was introduced by Newman and Girvan in 2003, where you try and sort of maximize links within a grouping and minimize links between a grouping. This is a social network for dolphins. He's a happy dolphin, obviously, with a lot of friends. Here, this is an automatic process to break this network of links down into little chunks. Now, our leap was to make this network an atomic network rather than a social network. The quantity that we had to optimize was this. I'll not go into great detail. It's basically a way of counting how interconnected the modules are compared to a null hypothesis of them being randomly connected. And you want to maximize the unexpected connectivity in these networks, and you permute through all the different possibilities. So you work through this. You maximize this queue. Now, it turns out there are choices here, because you've got a choice of the distance threshold. How do you decide whether an atom is connected or not? But you've also got a choice. You can actually tune this modularity function so you can bias more and more disconnected structures. So as you vary a knob which increases the number of self-loops in your network. The more self-loops you put in your network, the stronger the identity of a node or an atom to itself, the more individualistic that atom becomes, more island-like that atom becomes, and they break down the network. So on this far side here, this is like 5 self-loops, 4, and so on. So there's many, many self-loops here, very, very few here. As you go this way, the network decomposes into atoms eventually. We don't want that solution. We already know the decomposition into atoms. So we could just sweep along that parameter there, but we've also got the distance parameter here. And as you do that, you find a whole variety of different decompositions of the structure. So how do you choose the right one? Well, in this case here, what we did then is also try and minimize the amount of information required to describe the crystal structure in terms of these modules. So in particular, we strongly favored symmetric units with high point group symmetry. And this is what we're coloring here. This color here is how much information we need. So this is these dark brown cases, the lowest amount of information. Here are more complicated. It takes more lines of data to describe the structure in terms of these units. So it naturally picks out the icosahedron. This can now be automated. Okay, that actually was quite a simple situation. That's not why we're interested in this. There are other phases of boron. For example, the so-called beta boron, which has, well, they don't know exactly how many atoms it has in the unit cell, around 105 atoms in the unit cell, and quite a complicated structure. Just feeding, so you can probably see there are kind of icosahedral units in this system, but it's a bit hard to make sense of in the human eye. Feeding this structure into our algorithm spits out this decomposition. We find a whole bunch of pretty high symmetry subunits that we can pull it apart. Now, in principle, what I'd love to be able to do is then throw those units back together in a different way and found, I don't know, gamma boron or something, something beyond beta boron. Still, as I'll mention towards the end, this is a little bit outside of our regime, but that's where we're headed in this era. So it's automatically decomposing crystal structure. Okay, now I'm going to, for the final part of this talk, I'm going to focus a little bit on some applications. Think the fun we've had with this algorithm once we created it. So I'm a physicist and a very good collaborator of mine. The key collaborator of mine on this work is Richard Needs in Cambridge. And I was playing around with carbon structures and so on. And he said, can you do this at high pressure? In particular, can you do this for hydrogen at high pressure? Because I'll come back to that in a second, but this is a key problem in high pressure physics. And they didn't know the structures. And I answered, I said, I think so. And I'll show you the results of that in a little while. So what we got very involved in is high pressure research. What I've got here, what I put here is a few different, astronomical bodies. This is Titan, this is Earth, this is Jupiter, that's the Big Bang. And then these are the experimental apparatus that you use to explore these different regimes. This is Paul Macmillan's press in UCL. This is a diamond anvil cell, so they squeeze things between diamonds. This is the National Ignition Facility, which I'll say a bit more about later, and this is the Large Hadron Collider. Why have I put that in here? Well, we're talking about pushing atoms together. And that's really what they're doing as well in the Large Hadron Collider. Although they measure things in terms of energies, we measure things in terms of densities. Also, we're having to deal with effectively an infinite number of atoms, and they're just bouncing a couple of particles off each other. So we've got a much more difficult problem to deal with. But the idea is largely the same. So I'll say a little bit more about this National Ignition Facility in Jupiter. The pressure in the center of the Earth is 360 gigapascals. And diamond anvil cells can reach that. We can exceed that now in the lab. And so we can do quite a lot. We can figure out what is likely to be in the center of the Earth. The center of Jupiter is something like 10 terapascals, so over 10 times as great as that. And there's no sort of static apparatus that allows you to reach those pressures. However, this National Ignition Facility, which I sometimes describe as it's a sort of an inverse Death Star, in that it's the biggest laser in the world, but all the lasers point inwards into the center rather than outwards, destroying planets. And the nice thing is, actually, they're going to try and use this apparatus to try and simulate the behavior of matter in the center of planets. So there's a connection there. So this big sphere here there's lots of entry ports. There's measuring ports as well. These are people down here. They all fire into the very center. And I'll come back to that in a little bit later on. This will be central to one of the applications we had. So the first application we had was to silane at high pressure. And this was motivated because Neil Ashcroft, a condensed matter physicist, since the 1960s had been proposing that high-pressure hydrogen might be a room-temperature superconductor. This would be a big deal if you could manage to realize that. But the experimentalists were having trouble making metallic hydrogen, so he suggested maybe we should dope the hydrogen with something. Let's add a few other atoms of something else, and he suggested that you should maybe add a little bit of silicon, and maybe that will become a high-pressure, high-temperature superconductor. They published a paper, himself and Roel Hoffman, a Nobel Prize-winning chemist, suggested some possible structures for that, found out that, yes, indeed, this should be a high-temperature superconductor because they found a metal that had hydrogen in it, and hydrogen is light, and so the temperature should be high. We thought this was an excellent first application of our method. In fact, it's the paper in which we revealed the Ab Initio Random Structure method, but we rapidly found insulators that couldn't be superconductors. So we were able to, within a few months, respond to their publication and say, no, it's not a high-temperature superconductor. But I will come back to that. Neil Ashcroft, he really has the last laugh in this story. Other applications we had was, one day I was just trying nitrogen and hydrogen, and I got a solution that fell out of the random searches, which just looked wrong because I didn't have methane molecules. I had NH2 molecules and NH4 molecules, and that's not right because it's supposed to be methane. This was at 1 megabar or 100 gigapascals of pressure. Lots of careful testing later, we were able to propose this as a new state of ammonia, a high-pressure phase of ammonia. Now, ammonia is a component of these gas giant planets, so it's kind of interesting to people. So we proposed that ammonia was spontaneously ionized to form ammonium amide at 1 gigapascal. Very nicely, just 2 years ago now, there were 2 experimental papers where they confirmed that this indeed happens. But there was no suggestion in the literature that might happen before. This was a true computational discovery. It fell out of the calculations. Now, probably the biggest impact we've had in high-pressure physics is our contribution to the phases of hydrogen at high pressure. The results of this Ab Initio Random Structure Searching are probably the best candidate structures for hydrogen at high pressure on their route to, we haven't actually found metallic or superconducting hydrogen yet, but we're en route to that. We're sort of honing in on that. And now experimentalists we discovered this strange structure in one of our simulations. It was a mixed phase. It wasn't hydrogen molecules. It had sheets that looked a bit like graphene and molecules in between. We call this a mixed phase. This was, again, a bit of a weird solution to our in our simulations, but a few years later, this turned out to be an answer to an experimental conundrum where they actually found they were having different types of molecules in their simulations. Okay, so they were. This has made a big impact on that front. Other applications have been to aluminium at high pressure. We took these to extremely high pressure, multi-terapascal pressures, and we found that these complicated, incommensurate host-guest structures where you have tubes of atoms and chains of atoms all at different periodicities were coming out. This hasn't been found experimentally yet, but it's been chosen as sort of as a goal for the experiments that are done in this National Ignition Facility where they're trying to do shock compression of matter to extremely high pressure. So here's a few other applications. Recently we've published, we've predicted and worked with experimentalists to discover new xenon oxide phases. That's a bit surprising. Xenon's a noble gas. Why is it forming an oxide? Well, it's because we squeeze it to high pressure and make it do that. We found magnetism in unexpected places, for example, in potassium. We found that water, when we squeeze it to pressures that you might find in the center of Jupiter, isn't actually a good description of hydrogen and oxygen anymore. Water, H2O, will spontaneously decompose into hydrogen peroxide and something else, some hydrogen-rich sponge. This feeds into models of planetary models and so on. So they don't want to be modeling water at those pressures. Now this is actually very related to this answer here. So this result here. So H2O. Okay, if you go one down on the periodic table from H2O, you reach sulfur, H2S. And people have been doing experiments. Michael Ehrmann was doing experiments in Mainz in Germany on hydrogen sulfide, and he discovered, this is the big discovery, this is the validation of Neil Ashcroft's suggestion that maybe you could dope hydrogen with something else. He discovered superconductivity at 204 Kelvin. Now, fortunately, we'd been working on hydrogen sulfide as an extension of our hydrogen oxide results. So we were ready when this experimental result out to bang out a bunch of papers. So collaborations with my collaborators Yangming Ma in China and Francisco Mauri now in Rome and his group in Paris. We've been able to make quite important contributions to this. But in this case, this hydrogen sulfide superconductivity actually was suggested as a superconductor by a Chinese group doing structure prediction techniques as well. So now theory and experimentation is getting very much intertwined with each other. Okay, I'm just going to rattle through this example here. Now, carbon is a very material with a very rich variety of structure, from nanotubes to graphene to diamond to graphite, and this is a different kind of diamond, lonsdaleite and buckyballs there. There are many possible ways of putting carbon atoms together, and many of these have won people Nobel Prizes, for example, graphene and buckyballs and so on. But these structures are not thermodynamically stable structures. So the question might be, what are the other possible thermodynamically stable structures of carbon? Now, here was this picture appeared on the BBC News website at some years ago. An astronomer, this was his statement, they claimed that they'd found the universe's biggest diamond in the center of a white dwarf star. Okay, and the quote was, and I've redacted the name of the astronomer, "You would need a jeweler's loupe the size of the sun to grade this diamond," says the astronomer who led the team of researchers that discovered it. This worried me. How could diamond possibly exist in the center of white dwarf, which is very, very, very high pressure? Because diamond is a very open structure. There's lots of space in diamond. That should be squeezed away by the high pressure. So obviously, that's not really what they expect. If you ask them seriously, they didn't mean that when they said it. What they meant is a crystalline form of carbon. But it started a thought process, and I worked with my collaborator and postdoc, Miguel Martinez, and we asked the question, what's the ultimate state of carbon as we squeeze it to higher and higher pressures? And I forced him to increase the pressure each time by a factor of 10, and we got all the way up to 1 petapascal, which are kind of the pressures you find in a star. Okay? And we found actually 4 new thermodynamically stable phases of carbon, some of them rather exotic. Now, we struggled to publish this initially because the referees were telling us this was of no relevance to anything in the universe. Well, eventually we did manage to get it published, and shortly afterwards I was invited to Lawrence Livermore Lab, where they're trying to do laser fusion. And what they're doing is shining these lasers from the National Ignition Facility into these gold little cups here, shining them on a little carbon or a carbon-containing pellet, and it's basically a kind of a spherical rocket. So you bathe the outside of this pellet with radiation, intense radiation. The matter goes shooting off spherically, compressing the material down in the center and hopefully igniting fusion. But the problem is it wasn't working, and so they were interested in talking to me about phase transitions that might have been happening in their pellet on the way through. And indeed, they became very interested in that, and they've mapped out the full carbon phase diagram at these pressures now knowing that there are possible phase transitions. And they went on to do an experiment where they tried to confirm our theoretical results. Their curve was this blue curve, ours was this red dotted curve. They didn't prove our results. But what they'd actually done, probably, their experiments are very short-lived. And I'm giving the thermodynamic solution, which is the long-time solution. So actually, this has started a new iteration to try and understand how they can maybe slow down their experiments, or maybe how we could speed up our calculations and not necessarily seek the thermodynamic state. So it was mentioned on yesterday that we're going to have to stick with silicon, and this slide is just to show that actually there's more to silicon than might meet the eye, and this is a recent collaboration with a group that are blasting bits of silicon-containing compounds with a laser and forcing it to basically adopt a whole range, a plethora of metastable states, and then they were using electron diffraction to try and identify the different states. But they didn't know what to compare with, so we did some random structure searching and identified a whole slew of possible metastable, low-lying metastable states of silicon, and many of them they managed to identify in their experimental results. So we published this there. So potentially, there's, even just using the element silicon, there may be some scope for adjusting band gaps and so on. Now, I'm just going to finish off with challenges. I got one just a few seconds to say. I don't want to finish on a positive note. I want to finish on to tell you what the problems are. So random search, it does work fantastically. It's been a lot of fun. It allows you to discover a lot of things, but there really are challenges that remain. I mentioned that so far, if I put 105 boron atoms into my unit cell and run thousands or maybe millions of samples, I don't get the beta boron. So in order to get these kind of complicated structures, we have to think hierarchically to do that. It doesn't automatically drop out of this simple algorithm that I told you about. There are other complicated structures such as phosphorus. This is Hittorf's phosphorus here, which is really hasn't yet emerged from my calculations or anyone else's calculations. It was found experimentally. Other challenges are, for example, surface reconstructions. This is the famous 7x7 surface reconstruction on silicon. This contains a large number of atoms, and so far no one has without knowing the answer beforehand, managed to find this kind of structure. This is a quasi-crystal. you've probably heard about Penrose tilings and so on. There are materials, there are alloys that form essentially non-periodic arrangements of atoms. This is not currently accessible to this route. And a big challenge at the moment is if you look in the databases, about half the structures are actually disordered. They have compositional disorder. And at the moment, we're not treating that. That means we have to properly treat entropy and temperature and so on. And the other challenge is just the sheer size of compositional space. Now this can be divided. If you give you a bigger computer, can allow you to address that, but it's going to become expensive to properly search things out. So just to say, well, we're working on these kind of things. We're working on putting temperature into our predictions now. There's some very nice techniques coming out of Cambridge, out of Richard Need's group, and Bartolomeo Montserrat, allowing us to relatively efficiently put temperature back into our calculations. Configurational entropy still not properly dealt with. And I'll just finish off with what I'm working on right now with my postdoc, Gail Schusterich in Cambridge. As I've moved to a materials department, a materials scientist will tell you it's all well and good knowing the crystal structure, but actually what really affects the properties is microstructure. So we've started to try and investigate what happens when you interface structures with each other, try and find out what the atomic configuration in grain boundaries are. Here's a simple example of graphene interfacing with two different orientations of graphene, but also this is a much more complicated example of 2 bits of strontium titanate, which is quite complicated and very important material. What makes this really difficult is that we don't actually know what the composition is at the interface. So it is strontium titanate overall, but you can actually have some variations in the ratios between the strontium, titanium, and oxygen at that interface. The way that we tackle this is not by randomly moving every atom in the system. We place these portions of the structure up against each other. This encodes data that we've got from the electron microscopists who can tell us the angles at which these grain boundaries are forming, and then we just randomize the atoms in this smaller subspace of the job. Okay, so I'm just going to finish off now. I just want to, the messages are, this simple algorithm is really rather good, but really suited for this particular problem. It's not a general solution to global optimization, but the fact that you're putting random numbers in allows you to stumble on things that you didn't know beforehand. So it has allowed me as a frustrated experimentalist to have some of this joy of discovery that I'd been denied otherwise. And actually a very useful thing is to combine it with experiments. So I want to thank you. I want to thank Richard Needs and Georg, who are working with me on this in Cambridge at the moment. And this has been my generous funding over many years by the EPSRC. And actually, this being a computing-oriented conference, I really want to emphasize the importance of having good codes, of people who dedicate their lives to writing these codes. I'm not myself. The rest of my team that wrote this helped me write this CASTEP code. Without it, I don't think I'd have been able to do what I've done. So the time spent on code development really has paid off. And I thank you for your attention as well.